Hello guys, welcome to this video. In this video we will be continuing all our previous explorations about all the functions and developments that we did, and in this video we shall also find out more about the properties and all the different discoveries that we can make about this exact function and the distributions that we are studying. And meanwhile there would be a lot of solved problems as well, so just head forward to the video. We can start over from there. So we are given the integral m equals to 1 to infinity, n equals to 1 to infinity, m into n divided by m plus n whole factorial, and we have to prove that this is equals to 2 by 3 times e. Here e is defined as 1 plus 1 by 1 factorial plus 1 by 2 factorial plus 1 by 3 factorial plus dot 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 all the way up to infinity. Approximately this is something around 2.7. Anyways, like this is Euler's constant. So this series, let us name it as S. Now we are given two infinite series here, and we are given an summand. So this summand is basically the function which we are summing over. So basically f of m comma n would be mn divided by m plus n whole factorial. Here f of m comma n basically a function f with two inputs m and n. So it gives you an output which consists of m and n. So this series S, which we are calling it as S, we can write it as S equals to m equals to 1 to infinity, n equals to 1 to infinity, f of m comma n. So this is basically the series where f of mn is defined as follows. Now we want to imagine this series not in terms of an infinite series which has like two infinite double arguments, but rather we want to imagine this as a series which has an index which runs over m plus n. Now what I mean by this is, if we look at the indexes, we see that m runs over 1, 2, 3 and all the way, so all the natural numbers. Similarly n runs over 1, 2, 3 and all the natural numbers. Yeah, so like the set is natural numbers, so m belongs to natural numbers, n belongs to natural numbers. Now so this basically means that obviously what we do have here is m into n by m plus n whole factorial, and this function would assume all values of m and all values of n, and we would sum all of those terms together. What it means is, so let us take one by one. So since there are two infinite series, let us ignore this series for once, and let us only think that suppose this is given as n equals to 1 to infinity, where m is just a constant. Just ignore the m part. It's like m into n by m plus n whole factorial. So where like n is the only variable present. Now what happens is, when we put in n equals to 1, so this thing equals, put in n equals to 1, it will be m by m plus 1 whole factorial. Put in n equals to 2, it will be 2m by m plus 2 factorial. Similarly for 3, it should be 3m by m plus 3 factorial, right? So like in this way, this is basically a infinite series which consists only of the terms of m. Now think of it like this, that when we evaluate the inner infinite series, which was n equals to 1 to infinity, we are left with a function which only has terms of m in it, and we again need to sum this infinite series into an infinite series. So basically what we need to do is, we need to sum m equals to 1 to infinity, this whole thing which is m by m plus 1 factorial, 2m by m plus 2 factorial, please don't be sleepy, 3m by m plus 3 factorial, plus dot 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 all the way up to infinity. The thing is, if you become sleepy, I will sleep. So this is a very big problem. We need to stay focused. So like this, evaluating the inner infinite sum as n gives us this, and we know that this thing, this m equals to 1 to infinity, we had ignored it earlier, but right now we are bringing it back, and thus s would equal something like this. Now, what does it mean to have m equals to 1 to infinity as a summation, and what we are summing is also an infinite series? It basically means that we are summing all these values. So it will be a infinite number of infinite series. Does that make sense? Because this, like this one would be an m equals to 1 to infinity m by m plus 1 factorial, plus again m equals to 1 to infinity 2m by m plus 2 factorial, again that, like that. So it will be an infinite series. Now, a best or a better way, probably there could be a best way, but we would be talking about a better way of imagining things here. That consider we have this series m equals to 1 to infinity n equals to 1 to infinity mn by m plus n whole factorial. Now, what we want to do here is, since we see this m plus n term here, so that means whatever is the denominator will always be the sum of m and n, right? So what m plus n, what are the possible values of m plus n? What I need to find is what are the possible values of m plus n? Well, obviously m is 1 and n is 1, that is the least value of m and n. So m plus n's least value should be 2. It cannot be less than 2 because there is no 0, so 1 plus 0 would have been 0, but there is nothing like that. If m or n were 0, then obviously m plus n would be 1 plus 0 or 0 plus 1, it would be 1, but it is not 1, it is at least 2, because m is at least 1 and n is at least 1. And how many times does this value appear in the whole sum? Only once. Why is it so? Because there is only one instance where m will be 1 and n will be 1, and both of them will be put into the series. So the term, whatever the term 1 into 1 by 2 factorial, only appears once. Does this make sense? Because we are only concerned about how many values m plus n will take, or how many times will it take. So we see the first value that m plus n takes is 2, and we figure out the only way to get 2 is to have the value m1 and n1, and this is done basically when m is 1 and n is 1, and it will give you 2 factorial in the denominator, and the numerator would be m into n, which is 1 into 1. So this series, whatever it is, will have a term like this. It has to. And then again, what more values can m plus n take? Let's say, obviously m plus n can also take the value 3. But in what ways can it take? Well, it can take in only 2 ways, m equals to 2, n equals to 1, or it can take in m equals to 1, n equals to 2. These are the 2 ways m plus n equals to 3 is possible. There is no other way, because otherwise one of them, both of them has to be greater than or equal to 2, which will make it 4. So it's not possible. So at least one of them, exactly one of them has to be a 2, and exactly another one of them has to be a 1. Only then would the sum be 3. Now, so how many terms in this infinite series would be there where there would be a 1 by 3 factorial? So 2 terms will be there, and since we know the numerator is just m into n, so those 2 terms, one of them will have 2 into 1, and another them will be again 1 by 3 factorial, 1 into 2, basically 2 by 3 factorial, 2 times. So what we are trying to see here is a pattern. Basically, if m plus n, again let's take a last example, if 4, then how many ways this can be achieved? M equals to 1, n equals to 3, m equals to 2, n equals to 2, m equals to 3, n equals to 1. So this would basically mean that this term 1 by 4 factorial, as you can see in the infinite series we have a m plus n factorial. So 1 by 4 factorial will appear 3 times in total, and those 3 terms would be, one of them would be 1 into 3 by 4 factorial, one of them would be 3 into 1 by 4 factorial, and one of them would be 2 into 2 by 4 factorial. Now we want to generalize this idea, right? So what we are going to do is we are going to use something called substitution in infinite series, which is a method which we have heard basically in differentiation, in integration, where we substitute a variable and then we do the dx dy thing. But what we are going to do here is basically unique. It's not a standard method, it can only be done intuitively, and we are going to do that. So let m plus n equals to k be a new variable, but we do know that k's minimum value is 2, because m plus n's minimum value is 2. and m plus n assumes all values from 2, 3, 4, 5, everything, as we have seen up to 4. So this infinite series can be written as like this. The infinite series is m equals to 1 to infinity, n equals to 1 to infinity, m into n by m plus n whole factorial. It can be written as a big summation where m plus n is equals to k, and we are basically running this value from k equals to 2 to infinity. So we need this one inside. So k equals to 2 infinity, let it be the biggest summation, and inside let us find all such m and n such that m plus n equals to k, and we are going to sum mn by k factorial, because this k is basically m plus n and we have substituted m plus n as k. So there was an m plus n factorial which became k factorial. So what we needed, so observe in this one, m plus n has been substituted as k, so this became k factorial. But we know that the value of m plus n is such that it is minimum 2 and it can be any natural number after 2. So for every value of m plus n that it takes, like 2, 3, 4, what we did in the examples where we found out what m's does it correspond to, what m and n's does it correspond to, so that the sum is this. So we need to find out those values of m and n such that m plus n equals to k, and we need to sum mn over all of them. So basically what we need to do is k equals to 2 to infinity summation, and this summation indicates that m plus n equals to k, those m plus n where m plus n equals to k and m greater than equal to 1 and n greater than equal to 1, and we need to sum all those values m into n. And this is a pretty easy procedure, because whenever you have m plus n equals to k, the only possible values are m equals to 1, n equals to k minus 1, m equals to 2, n equals to k minus 2, and all the way up to m equals to k minus 1 and n equals to 1, like this. So what we can do is we can write k equals to 2 to infinity summation r equals to, so it goes from 1 to k minus 1. So basically we can write r equals to 1 to k minus 1. M can be r and n can be k minus r. So you see, r plus k minus r is always k. So r is our m, k minus r is our n, such that m plus n is always k. If we add this to it, always becomes k, and there are k minus 1 such values. Now this, so the resulting series is k equals to 2 to infinity, r equals to 1 to k minus 1, r into k minus r. Now call this series as some tk. Let us evaluate tk, and tk is a finite summation because it does not have any infinite summation in it. Tk is a summation which depends on k, because it is from r equals to 1 to k minus 1, and inside we have r into k minus r. We can distribute this to as rk minus r square, and we can write this one as k is a constant in the first summation because the summation variable is r. We can write this as k into r equals to 1 to k minus 1 r, and this second summation as minus summation r equals to 1 to k minus 1 r squared. This is basically sum of the natural numbers from 1 to k minus 1, this summation, because it only means 1 plus 2 all the way up to k minus 1. And this summation is basically the sum of the squares up to k minus 1 whole square. Now applying the formula for this is basically k minus 1 into k by 2. And for this one, this is k minus 1 into k into 2k minus 2 plus 1 by 6. Let us simplify it a bit. It will become k square into k minus 1 by 2 minus k into k minus 1 into 2k minus 1 by 6. K and k into k minus 1 goes common. So anyways, we can put it back here. So what we need, this is tk basically. This is tk. So tk is equal to k square into k minus 1 by 2 minus k into k minus 1 into 2k minus 1 by 6. And what we need to do is we need to we know that our sum s was basically, because we took this one as tk, and there was an 1 by k factorial here. There would be a 1 by k factorial here because of the 1 by m plus n factorial here. So our required sum is just k equals to 2 to infinity tk by k factorial. So we have successfully converted our double sum into a single sum, and now this is just a matter of time because this is basically k equals to 2 to infinity. Let us just evaluate this one first. K square into k minus 1 by 2 into k factorial minus some g, let's say. This one would be g, so let us evaluate this one first. So there are two summations. So the first of them would be k equals to 2 to infinity k square into k minus 1 by 2k factorial. This would give you the k and k cuts off. It will be k equals to 2 to infinity k into k minus 1 by k minus 1 factorial. And this k minus 1 and k minus 1 cuts off. It will be k equals to 2 to infinity k by 2 into k minus 2 factorial, right? And what we can do is this, k equals to 2 to infinity. First let us do this. This k equals to 2 and it also starts from 2. Basically this sum is like this. It's like 2 by 2 into 0 factorial plus 3 by 2 into 1 factorial, like this. We can write it rather as k equals to 0 to infinity k plus 2 in the numerator and 2 into k factorial in the denominator. It's basically the same thing. The numerator will start from 2 and the denominator will start from 0 factorial. It's just a change of index of the variable, and this would give you k equals to 0 to infinity. So we distributively divide it into two parts, k by 2k factorial and 2 by 2k factorial. So k by 2k factorial plus k equals to 0 to infinity 2 by 2k factorial. So k by k factorial is basically k by k minus, it's by like 1 by k minus 1 factorial. This is basically equals to e by 2, and this one 2 and 2 cuts off, it's basically equals to e. So it's 3 by 2e, this part. Let's do this part, k into k minus 1 into k minus 1 part. So this becomes, therefore g is equals to k equals to 0 to infinity k into k minus 1 into 2k minus 1 by it was 6 into k factorial. It should be k equals to 2 to infinity. K and k cut off, it will be k minus 1 factorial, and k minus 1 and k minus 1 cut off, it would be k minus 2 whole factorial. So the sum becomes k equals to 2 to infinity 2k minus 1 by 6 into k minus 2 whole factorial. So what we did here was we cut off k with k factorial. So k factorial is basically k into k minus 1 factorial, and then again k minus 1 factorial cut off to give you a k minus 2 factorial. Again the denominator starts with a 0 factorial, so we can rearrange k to find it from k equals to 0 to infinity and increase this k by 2, that is 2 into k plus 2 minus 1 by 6k factorial, and we get k equals to 0 to infinity 2k plus this is 2 4 minus 1 3 by 6k factorial, and this would give you 1 by 3 into summation of k equals to 0 to infinity. This 2k by 6k factorial is 1 by k minus 1 factorial, and this the next one is 1 by 2 into k equals to 0 to infinity 1 by k factorial. This is 1 by 3e, this is 1 by 2e. This would give us 5 by 6e. Therefore our sum is basically, the previous answer was 3 by 2e and this is 5 by 6e. Let us try to see if the answer is correct. 3 by 2e minus 5 by 6e, it would be 9e by 6, I think, minus 5e by 6. This is 4e by 6. This is 2e by 3. And somehow we have got the correct answer, which we were supposed to prove. So this would complete our investigation for this series. In the next one we also would provide a triple series of the same kind. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives, There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes, where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.